But here's a serious trusted advisor. Why does large language models hallucinate? You know that from ChatGPT, you know that from Copilot, you know that from almost any large language model, even the very advanced models from today, they hallucinate. Why? Today we will go a little bit deeper into that question, and we will discover a lot of technical stuff on our way to the answer. So we will touch ragging, we will touch how Microsoft does countermeasures against security stuff and against hallucination and so on. And we will learn about the 3 ways how to adapt to a large language model. Let's go. Before we get into the solutions, let's first understand the problem. A large language model like, I don't know, GPT-4, you name it, was mainly trained by the internet. So let's draw that. Drawing is always helpful. So we have the training path here, training. And this is the past, right? Training happens first. So any model, let's take GPT-4 because it's a little bit older, was trained until a specific point. GPT-4, for example, with the internet as of 2023, with books, with Wikipedia, with code, everything, you name it. So all this is like the input. In the training process. Training happens. At that point, once the training is done, the LLM is like frozen. So the output of that training is a large language model, but from now on, it's frozen. It's like done. Right? So you have billions of parameters. And also these billions of parameters are frozen. Because they were trained and that's it, right? So you have basically 2 different problems. So the first one is something the model, let's take that right, doesn't know. Something. Yeah? So for example, questions about your data. Model doesn't know your data. The model will always give you an answer. So this leads to hallucination. Second way is too old. Something that is not correct anymore, right? So for example, you ask about something there you go. Something about 2025. Some news, right? So you will get an outdated answer. Not good. The second, as a third problem, could be never seen. So you ask the model about something that the model has never seen. So let's say about internal processes. Then the model will make up some facts. Because you will get always an answer, but the answer is not really helpful, right? So you will have hallucinations, you will have like made up answers, and you will also kind of feel it or see it on the level of detail. When the model stays very high level, usually you either didn't ask the question right or the knowledge is very thin. When the model is able to get much more into details, then you ask the correct questions or the question in the correct way, or there is a lot of detail or both, hopefully. So the large language models are like knowledge snapshots from one, like a photo from one point in history. They only know what's in their training. And when you ask something that is out of the training scope, it could happen that they say, I don't know, I'm sorry. But you will get one kind of answer, and this answer could be not straight, I don't know, but this is like this and this, or I assume this is like, and so on. So it goes into the direction of hallucinations. The model trainers do a lot against hallucinations. So models are getting better and saying, hey, I don't know. But since they don't know anything in the end, they are statistic machines, it's hard to say, I don't know, because they have no knowledge about the meaning of stuff. Right? So the large language models don't know about your data, right? In the end, all the three problems point out that doesn't know, something is too old, never seen. So they should know something to answer your question, but they don't know. What can we do? How can we find out of this way? So it's basically three solution paths. Let's draw them. Solution paths. Three solution paths. So first one, right? So problem is the large language model doesn't know, for whatever reason, right? We have this base LLM, like GPT-4, for example, and we have three solution paths. The first solution path could be fine-tuning. Fine-tuning would mean, oh wow, that's crazy. You retrain the model. Retrain the model with zero data, right? So that's possible. Of course, the large language models are a big investment, but you can create your specialized model, and there can be good reasons to create specialized models just for your purpose. Absolutely. But then you are a little bit back in the old days, because it's your own risk. You need your own training data and so on. You are responsible for your quality, all that stuff. Then we are in the area of Azure machine learning, where you can train your very own model. The second solution path, of course, this is costly and there's some risk attached. The second way would be RAG, Retrieval Augmented Generation. That means you give the large language model the context at runtime. Runtime is the important part here. So you give your relevant documents. You say, hey, here are your documents. Please give me the answer. In Fabric, this would be data agent. And the first and most obvious solution, and it hits a lot of these problems, is prompt engineering. Prompt engineering means, to some degree, you ask the wrong question or you ask the question wrong. So you ask too generic, So basically you ask, hey, where can I go today, right? You don't provide a location. You don't provide something what is today. You don't provide anything about your interests, about your hobbies and so on. So it's for the model, it can just guess something. You say, okay, that's crap, not helpful, right? That's for example, you could provide examples in prompts. Yeah. This is a correct answer. This is not a correct answer. Something that says helps a lot. It's really fast. That's a benefit. You don't need any data. It's just improvement, right? The copilots do a lot of this by default. So they enrich your prompt quite a lot behind the scenes. So you get, so to say, much better answers than you should get based on your question. Because in almost all cases, your question is too short. You can play around when you have something like ChatGPT or even Copilot. You can ask, hey, what could I ask better in my question? How could I improve my question so you can understand my question better than before? And this is a very, very nice way to get some input and to get an idea what you could improve and to learn for the next prompts you could that you put in. So this is like a little bit like checked, not completely. It's always worth to go into prompt engineering, to my experience. This is for us out of scope. So fine-tuning and training models at the moment not in scope. And this is the interesting point. There we are in the fabric space, ragging your agent with data, giving the agent more data to answer your questions better is absolutely the main domain for Microsoft Fabric. To understand RAG, we need to understand embeddings. Once we have understood embeddings, it will be much easier to get the maximum out of ragging. In the first part of our video, we learned that all tokens are IDs. Equal ID. So for example, the token lakehouse equals the ID, let's say 1, 2, 3, 4, 5. This is not true, not important. Just a number. The embeddings go a little bit further. They are not just numbers, they are meanings. So an embedding vector is a list of numbers. So you get out of that numbers, it's a list of numbers. And a model like text embedding ADA002 produces like 1536 dimensions out of that vectors. So let's have a look how that looks in a graphical way. So you have your data storage. Let's say Fabric. And you make a find similar search. Find and find similar means, for example, lakehouse is similar to warehouse. Not identical, but it's similar. But report is too far away. Of course, it depends on the distance, right? But in this case, report is far apart in the vector space. Completely different concepts between lakehouse and report, but similar concepts between lakehouse and warehouse. Both store data. So in the vector space, they are like close together. So how exactly do we measure close? Close. Oh. Draw that in green. It's much more logical. There you go. But how do we measure close? This is with cosine similarity. So it's a value between 0 and 1. Something between 0 and 1. So which essentially means 0.95 means very similar, and 0.3 means it's barely related. So lakehouse and warehouse have an proximity, for example, of 0.95, and lakehouse and report have a proximity of 0.42. Not so good. So this is like the close is like the cosine similarity. So now it's like the heart, right? The key insight. When you ask something, because you have this prompt, right? So you write your prompt, the large language model gives the answer, which is a prompt from the large language model point of view. So it's like a chat, right? So that's why the famous name ChatGPT. So when you ask something like, let's say this is a question, how do I store data? Your question also becomes an embedding. And that's like the key. Let's have a practical look on that. I've created a short, simple Python notebook in Microsoft Fabric with these 7 texts. And we will visualize the locations in the vector space in the large language model. So 7 texts, each with 384 dimensions. It's a very simple model, but that's okay. And we will see the different groups, because all sentences have a semantic relationship, so they should show up more or less close to each other. This is running in the Fabric notebook, so it needs to install all the dependencies. The first output is a simple sentence count with the dimensions. There it is already, embedding dimension 7, 384. That's it. Yeah. And now it's running cell 2. And cell 2 will give us a nice visualization. And we should see 3 different clusters that are more or less good distinguished from each other. That's a scatter plot. So the semantic space, so to say, fabric versus pizza. Because some sentences did cover the topic pizza and others did cover the topic fabric, which is obviously different. So run list is completed, and there's our graph. And you see the pizza is on the top left, it's in red. The fabric stuff is mostly on the right side. This is a scatter plot. And the like mixed content is on the lower side. There you see the pizza area, the semantic space. The pizza is clearly distinguished. Lake house and Delta Lake is near by each other. Fabric warehouse is optimized, is a little bit more on the left. And Microsoft Fabric in general, the green ones are on the lower side. So this is really nicely distinguished, and I think it's a good way to get it a little bit visualized. And then we can search which kind of documents have a similar embedding. And this is called vector search or semantic search. In Azure, this is the Azure AI search. This is a vector-based search. It is much better than keyword search because it to some degree feels as if it would understand a meaning. So now we have all the puzzle pieces. Now it's time for ragging. So let's have a look at ragging. Let's start with our drawing. So first, rag. That's a nice G. It's my G, but it doesn't look good here. So let's draw a nicer G. Rag. So first we have preparation. Preparation means your document PDF, Word, Wiki, you name it. Your documents are then chunked into 500 to 1,000 tokens. And then the embeddings are created. And these embeddings are then stored in the vector store. Okay, works. So this is like preparation. This preparation then goes into runtime. The runtime is per question. So think about the chat. It's chat and answer and chat and answer. And for every question, we are talking about runtime. Per question. That's second. Okay, what happens in the runtime? First is retrieval. User asks top products. User asks, of course, a better prompt, but let's take it short. Top products. Top products goes to the query, is converted to an embedding. This is then put into vector search. The vector search is related to our vector search vector store. So let's draw a line from the vector store to vector search. And the result are the top 3 to 5 chunks. These chunks are the 500 to 1,000 token items out of your documents. So this ends up in second phase. Second phase is augmentation. Augmentation means the prompt is extended. With context, chunks, and the question. Top products. So this is the augmentation. Phase 2. Inside of the runtime 2, right? So this is first one, retrieval. Second one, augmentation. Third one, you guess it, generation. Generation means that we use Azure OpenAI. Let's say with GPT-4 or whatever. And the answer is formulated out of this augmented prompt with real facts. So this is part 3 of the second step. So first step is preparation. The second step is runtime. And these work both together to make ragging possible. So first, we get your documents, we split them into chunks, right, with overlap. There's always an overlap, so a sentence don't get cut off. And then it went into the runtime with first retrieval. The question becomes an embedding with augmentation. Then the found chunks are inserted into the prompt. Like here's the context, chunk 1, chunk 2, chunk 3 for that question, top product. And third one is the large language model generates an answer out of that chunks and your question, but now with real facts. The trick here is the large language model wasn't trained. It gets the information at runtime, so it's really current, and it's basically your data. It's always current and it's always using your data. So that's ragging. So to make this chunking a little bit more visible, it's very simple. So let's say you have an original document with 10,000 tokens. Let's say that the document with introduction, with products, with customers, etc. Not really important. 10,000 chunks, tokens. So now the chunking happens. Chunk 1 is 500 tokens plus 50 tokens overlap to don't cut off sentences. Chunk 2, the same, 500 plus 50. Chunk 3, the same, 500 plus 50. You get it. So this is like the chunked document that is then stored for retrieval in the vector database. So that works, but well, Copilot does use a lot of RAG, but instead of document chunks, Copilot is using your schema. When you ask Copilot, show top products, let's say Power BI Copilot, then the grounding automatically collects your schema, products, ID, revenue, and so on, the DAX measures, the chat history, the meta prompt, and all that is automatically inserted into the prompt. So this is augmentation. This works exactly like ragging. Remember, like the augmentation here. This, the second step, right? So the extended prompt, there Copilot jumps in and puts in your data, but of course Copilot doesn't need to index each DAX query in a vector index. That means Copilot have different groundings. So when we have a look at the different Copilots, we have Copilot for Power BI. We have Copilot for Warehouse, just an example, and we have Copilot for Notebooks. There are more Copilots than Fabric, I know. And we have the schema. We have measures. And we have the chat history. So what is collected where? Power BI collects your schema. Warehouse collects your schema. Notebook doesn't really collect your schema, but they use the data frames. Measures are only available in DAX, so this works only for Power BI and for Copilot and Power BI. And the chat history is collected on all 3 Copilots. So you get a little bit an idea. Let's have a deeper look on how Copilot really collects your data. User prompt, show top products. User. There we go. So first of all, there is a thing called auto grounding. Which means Copilot can select essentially your schema, the text measures, the chat history, and the meta prompt defined by Microsoft. You are a helpful agent and so on. So the complete prompt is assembled through the schema, the text measures, the history, and the meta prompt. Right? Meta prompt, you are a helpful agent, schema, your products, measures, the total revenue, chat history, everything you talked with the Copilot. So let's assemble that in real. So meta means you are. Schema means products, as an example. The measures, total revenue, and the history. Plus, of course, the user prompt, top products. All this is the complete prompt in Copilot with auto grounding. Then this is, like in the schema above, given to Azure OpenAI with GPT-4, 4.5, 5, you name it, and might result, for example, in a SQL query, select something from. So this is essentially the response. Copilot sees the structure, not the data, right? Different Copilots have different groundings, and hidden columns are not in grounding, and row level security and all other security is respected. The Copilot filters everything out that you are not allowed to see. Let's have a look at the data agent. I have brought a very simple lakehouse, and we will only use one table, which is essentially a sales table with the usual suspects like unit price and date and so on. The dates are around 2013, 2014, 2012. So let's create a data agent to chat your data. And we can, well, give it a name. In this case, it's a demonstration name. That's okay. There are some error messages popping up from my previous test. Let's select the correct warehouse, and we will tick only the sales table. And well, now what happens in the background is that the data agent is like ragged with our data. We will simply ask analyze recent data for any outliers, and now it's analyzing the data. Maybe we will see in a second that takes a little bit of time, but it's interesting that we can really cover the genesis of that. So this is I have no idea basically. When we copy the prompt and rerun it, then it will not work again. So it will take one more time. But you see the prompt is much more enhanced now. compared to the previous ones. And so there is more information. This is the enhanced prompt that we already see there. But still it fails, and I've cut it off because it took some minutes to analyze, and I precised it a little bit about 2013, which speeded the things up. You see it's all again an enriched prompt, and now we will get 2 results. So it works. This is a formatted results by large language model. And when we have a look, we will see that there is SQL code generated in the background, which makes the magic. This leads us a little bit to the question, how about responsible AI? You know, AI doesn't really have a sense about meaning. So AI could tell you everything, whether it's true or not. So it's very, very important that you have good security guardrails to prevent you from, getting wrong or bad answers. So let's have a look how that looks. So bad answers would mean hate speech, for example, or violence or self-harm or something like that. So we have the user input. This is the user prompt. So layer 1 of defense of responsible AI is responsible AI. Layer 1 is input filter. So first there is the content safety API that filters a lot out. When you go through this and everything is okay, then that's fine. When you go through this and it's not fine, then you get blocked. This checks for hate speech, violence, self-harm, and so on, sexual content, all that stuff. The next one, next guardrail is layer 2 to meta prompt. Meta prompts checks for legal advice, medical advice, topic, so stay focused, right? So when you go through this, that's great. This is not a block by definition, but this will influence the answer. So it might happen that you ask something and you don't get much details back on that. Next one then are the system instructions here. And then the layer 3 is a large language model, which means the model itself is trained for safety. Azure AI is trained for RLHF, it's abbreviation. So that's security measures. So the model itself looks for security, but that's layer 3, right? And layer 4 is the output filter. So your output then is assembled. Layer 4, output. And the response is again sent through the content safety API. There it can be blocked again, or it's okay. So, and then the response is delivered to the user. Layer 4 checks especially for hallucination. For harmful content. And for PII, personal data leaks. This is layer 4. So this is like the responsible AI. So this is taken very seriously, obviously. What you cannot control, by the way, let's go through that with a different color, yellow. So you can control the system instructions when you use data agent, for example. They can write the system instructions. You cannot control the meta prompt. You cannot control the content safety API. You cannot control the large language model internal safety checking, and you cannot control the final content safety check. So that's all not possible. So we talked a little bit about data agent. Data agent is a built-in capability. And we talked about RAGing in general. So there might be the question, when should I go with data agent? Because of course it's pre-built, it's very easy to use, but it also has limitations. And when should I go with my very own RAGing, right? So question is, I need RAG for my fabric data. That's a big question. Which way to go? So first question is schema grounding sufficient? So or other way around, is your schema good enough that the data agent can read something out of that schema or not? Yeah? First question. So left is no. No means I need the real data. Yes. Then you are good to go with Copilot and Fabric. Next question is, do you have structured data? Oh, structured data. Let's say, yes, you have structured data. Yes. Then your solution is data agent. It just works. It works really well out of the box. Let's say, no, I don't have structured data. Next question is, do you have external documents? Outside of Fabric. Then you say, no, everything is in Fabric. You can still go with data agent, because data agent can use multiple sources. When you say, yes, I have external documents that are not in some way mirror, shortcut, you name it, available inside of Fabric, then next question is, do you need full control over chunks, etc.? When you say yes, then you are at custom RAG. So this is like build your own data agent. And you say, no, I don't need any kind of control. There might be a chance that you can make the data still available in Fabric. And if that is possible, then you still can use data agent. Well, that's like the decision flow. But basically, you see the main question is, a schema grounding sufficient? Most probably not in Fabric. And the next important question is, do we have only structured data? Then you are on the data agent side. And I would expect that most data in Fabric as of today is very well structured. So you will deal most probably with structured data. So this was like part 2 of our AI Foundation series. Now you know why do large language models hallucinate, the 3 different solution passes like prompt engineering, ragging, and fine-tuning, how embedding turns meaning into numbers, how ragging works with chunking, with vector search, with augmentation, the Copilot data agent ragging into integration into Microsoft Fabric, and how Microsoft itself does a lot of for responsible AI to protect you from wrong answers, harmful answers, and so on. In the next year, we will build on top of that with configuring data agents, with vector search with Fabric, and integration with Azure AI Foundry. If this video helped you and you want to get notified when the new episodes come out, thumbs up and subscribe. Happy holidays and see you in 2026. Bye.